My name is Angus, Angus Fletcher. I work for Serenova, which is a company based out of Austin, Texas, and out of sunny Fredericton, New Brunswick, Canada. I took this a couple months ago. We went for a bike ride on a nice day. P.S. I really like bikes. I got a chance to do a little bit of cycling down here. That's the ride that I took down. I have a lot of bikes, and I have invented a function to determine how many bikes a person should have. This one's public domain. You can just have it. It's this. So, highly sophisticated, but very important. Okay, but for real though, we should probably talk about what I came here to talk about. I am talking about emulators, and I'm going to start with some of the inspirations that got me into this. So, about 2 years ago, I was reading Racing the Beam, which is a book by Ian Bogost and Nick Muntford, and they were kind of getting into this idea of doing what was called platform criticism, which is sort of like they wanted to do critical theory for games, and so they wrote a book that's sort of like 50% hardware analysis and 50% stories about people making games, which I'm really into this stuff. I like the idea of sort of beautiful and interesting technical writing where people try to write about the technical but in sort of an accidental or unusual way. And so that book got me really into it. And the title refers to a really interesting phenomenon with the 2600, which is that there were in its video chip only 3 registers, or 1 register for sprite, and then there was one for like player A and one for missile, which is just for projectiles. And so if you wanted to draw multiple sprites in a row, you actually had to kind of cheat. And in a feat of mutability, what you would have to do is change stuff in that particular register while things were drawing. So you had to essentially sync your code up with how the video stuff worked, hence beam racing. So I think that's really cool. I don't know about you, but this is a prominent example in Space Invaders. You can notice that in each of the rows, all of the sprites are the same, and that's not a coincidence. The programmers would shift the sprite location in concert with the graphics renderer to copy it horizontally across the screen. Due to the limitations of the hardware, this sort of hack was necessary to create games beyond a certain level of complexity, and it required like a little bit of ingenuity to sort of figure this out. And these limitations and methods really jumped out at me too. I like this stuff. I like when people have to sort of come up with ingenious ways to work around things, and that particularly I thought was really cool, and I was like, maybe I should learn a little bit more about how computers work. So the other good thing about these computers is that they're actually like quite a bit simpler than anything that we use today. Like right now, there's no one person who can dive into a chip that they have and say, this is something we understand. They're essentially, you have teams of hundreds of computer-aided city planners that try and lay out these chips. The 6502, which is the chip that inhabited the Atari 2600, was laid out by a single person on paper and checked with a ruler before they did anything with it, right? So they did that, and then they took it and they put it onto some acetate, and then they used that acetate to etch the chip. So there literally would be people crawling around on a table trying not to mark up this giant transparency so that they could put transistors in the right place. I have no words for it, but I was inspired for sure. And the teams of creators were really small too. Usually games were made by 1 or 2 people in a couple months. For example, E.T., I think, was made in 3 months and then promptly abandoned because it arguably almost ruined the video game industry. So I didn't want to go too hard on wizard slides, but only because I figured that Ramsey would have it covered. But now some TSA official is going to be really confused because business wizard is in my search history. But whenever I encounter anything new in computing, I usually think it's kind of magic. Like, graphics are still magic to me. For a long time, I thought that security was complete wizardry. And there's just a lot of stuff that seems opaque and daunting, and you're like, how do people actually do this? You have no idea. And then slowly I sort of pull at the thread and start reading about something, and it starts coming together. And that is absolutely how I felt about emulation. I'd probably done, 20 hours of assembly programming in my entire life up to this point. Most of it was in school, and most of it was on machines that were built for pedagogical reasons and not for actual use. Having my whopping 20 hours of experience, I was like, I know how register-based machines work well enough to do this, probably. So at around the same time, I was also reading and watching David Nolan's work around Ohm, and it immediately captured me, specifically these two ideas. One was making interactive systems declarative, taking things that are sort of stateful and side effecty and trying to model them in an immutable way, and then to sort of split the operations you do into two separate kind of streams, one being querying, which is declarative, you're just looking for paths 90% of the time, and then the other is transactions, where you're actually making changes. So it led me to start thinking what other systems we might be able to build this way. I'm not a front-end dev by trade, so when I see some of this stuff and how nicely that code is now written and represented, it kind of blows me away. And so, I wanted to see if I could do this in maybe a different context. And then the other thing that I thought was really cool was in the to-do MVC demo, there was like a slide or something in a blog post or something. It was like time travel in 6 lines of code. Like, you just add a watch to an atom and call it a day, which is just really cool. Like, I've like been writing Clojure for a couple of years now, so maybe I'm a little bit more jaded about it. It's like, time travel, yeah, whatever, so what. But also, it's pretty cool. So the other thing that I was kind of following was tool-assisted speedrunning community, which is a group of people who use emulators to complete games in as little time as possible. Because they can step through frame by frame, it's possible to take advantage of all sorts of ridiculous timing issues and bugs like the one shown above. I probably could have given an hour-long talk with just like GIFs of weird stuff that happens in games, but I found at least one good one. And they're interesting. They're cheeky and subversive in their way. They're a celebration of loopholes. They're something that bring free-form play to games that can otherwise be prescriptive and rigid. They're also painfully handcrafted by manipulating a game frame by frame, discovering and exploiting tricks. It's gameplay by research and debugger. It's a really unusual way to play games. It's like, I'm trying to think. I don't know, it's weird. It's just like, it's over-engineered in the most pleasing way possible. So anyways, I figured, all right, well, let's just take these ideas and kind of squish them together, and maybe we can see what we can do and build a time-traveling emulator. Excellent. So now I'm very excited. This is the first time I get to do a definition slide. So I'm just gonna soak it in. But emulate is from emulus, meaning to rival, or to match or surpass, usually through imitation. It's about building a system that imitates another, with the key point being imitation. The more you get into emulation, you realize that, for the most part, direct accuracy is not necessarily the goal. In the same way that, like, again, graphics is magic to me, so I can't speak to it, but in the same way that graphics isn't about one-to-one simulation of physics, emulation is not about one-to-one simulation of the machine you're trying to imitate. So rather than creating a perfect image of our desired system, sometimes we're creating a roughly rendered facsimile. So I don't really have much of a connection to the Atari 2600, so I wanted to try something from roughly that area, but something that I had a closer connection to. So I decided to imitate the NES. So some very, very brief history about the NES. It was released in Japan in July of 1983 as the Famicom, or the Family Computer. It was then released in the US in 1985 as the Nintendo Entertainment System. Anecdotally, it might have actually saved the video game market, which crashed in 1983 after E.T. was buried in the desert. Which is a very good story. I'll tell it later if you want to know. It had the Ricoh 2A03, which is a very similar processor to the 6502, which I'll talk about in a moment. Yeah, let's get started. So first I was trying to figure out how to learn how to imitate. This is a project that is not like a lot of the things that I built. Normally, when you're designing a system, you try and find all of these decisions that sort of lay together, or you write a spec and then you do something. But in this case, that's not what we're doing, right? The spec already exists, and the spec is a physical artifact. The problem is that I can't just get requirements out of it, right? Like, I don't even have an NES, so I essentially have to build everything by hearsay, more or less. It's like trying to imitate a drawing, but you only have other people's description. So I guess it's like being like I forget what that's called, a criminal drawer. So the first thing that I had to do was try and come up with a model for the thing that I was trying to imitate, and that meant a ton of reading. Luckily, there are a few decades of documents that helped me put together a picture of what I was looking at. And those sources are from all over the place. Very little information came from directly from the manufacturer. Surprisingly. So most of it is documentation of similar systems or the result of people's reverse engineering efforts. So a lot of the most useful information comes from text files from the 90s and the aughts. I have like probably 4 or 5 PDFs of 6502 programming manuals on my computer now, which are really, really fun to look at also because all of the diagrams for how things behave they were typewritten, so there's like typewriter ASCII art in them, which is really great. So that was the first thing I decided I would model would be the CPU. So the CPU is the Ricoh 2A03, which I mentioned before. It's got a subset of the functionality of the 6502, which is fortunate because, as I mentioned, the 6502 is incredibly well documented. So it has 3 registers, A, X, and Y. A is the only register that can do all of the math. X and Y are mostly placeholder registers. Not placeholders, but they do stuff, they just don't do all the math stuff. And those are all, note that most of these registers are just a byte, right, because this is an 8-bit system. We have 1 byte of status flags, which we'll get into in a second. We have some interrupt handling logic. We have a program counter that tells us where we are. We have a stack that allows for subroutines and returns, and a stack pointer, which tells us where we are on the stack. And then we have an instruction set of 56 opcodes and 11 addressing modes. There are also some undocumented opcodes. Most of them crash the system, some of them don't. To support every game, you have to also support every programmer who decided that an undocumented opcode is a really good idea. Thanks, guys. So this is our first picture, and it's mostly of the CPU and a few registers and some memory and a program counter. And right now, that is basically what it looks like, right? So we have our registers. We have the PC, which is going to be a byte. We have the stack pointer, which is also a byte. And then we have the flags, these very, very well-named flags, C through N, being carry, 0, interrupt disabled, binary coded decimal, which we actually don't use. This is actually the thing that was stripped out of the 2A03. The 6502 has binary coded decimal. We don't have it, but we have to support the flags, so it's there. Overflow, negative, and memory, which currently is an array of bytes, but we're going to get into something a little bit more advanced afterwards. So basically what we're trying to do is we want to find a byte at the program counter. We want to look it up. We want to resolve some address stuff as well, because the addressing modes all behave differently. And then we want to apply changes to the state. And so this is sort of, this isn't a function, but this is how the data flows. And so when I mentioned Ramsey's talk before, this is kind of a backwards version of that, where I'm taking, at the bottom I have this assembly code, machine code, and I'm turning it into these Clojure maps, or an array of Clojure maps that we can work with. So in this case, this is and 0 specifically, and immediate 0. So what this does is I take the argument 0 and I AND it with the accumulator, which will 0 out my accumulator. So I read it, and I have just a very, very big lookup table that shows what all these opcodes map to. I'll be happy to show it afterwards during questions or later on if you, it's also on GitHub, I guess. But and then we have one argument, and we get a certain number of arguments. So we look up the opcode, and we see the function there. We see the address mode is set to immediate. We have the number of bytes read and the number of cycles that this is going to take. We don't care about the cycles yet, but we will. After we do some augmenting with the address mode, we have another function that goes away and reaches into memory and resolves our arguments from memory so that we can make our changes to state. So the way that looks is basically we have a map lookup, we have a multi-method, and then we have a second multi-method for actually executing the operation, and that looks like this. So we take the state, which is our just big map of state. I showed you the sort of simplified version of that model. And then we take the operation and we apply all of these things to the state. So that cond arrow, I promise actually should be there. I just deleted something that we don't care about right now so that the slide would fit. But all of these gets and sets, I wrote just a ton of these tiny functions, and it was basically because I changed my memory representation or my internal representation 3 or 4 times, and I didn't want to do that anymore, so I wrote, I accidentally wrote a language, I guess. Yeah, so that's basically what it looks like when we execute that. So this is a fun thing where we have to do arithmetic, and I thought, okay, well, cool, we have the Clojure core library, so we can just use all of the bitwise operators there, and that'll be fine, right? But no, because if we are using an 8-bit number, some things won't work because 8-bit assumes overflow at certain points. So that means that we have to write some of those arithmetic functions ourselves. That is not actually as hard as I thought, and spec was a really big win here because I can write things like this. So this is arithmetic shift right, or arithmetic shift left. And carry is not a good name for that thing in this situation, but I, like, while messing around in the REPL with the spec, I sort of converged on this thing, and the little function invariant here basically says, like, if you shift something to the left, the result will either be bigger or you'll get a carry. And you can actually be even more specific with that spec and say that it will either be double and you'll get a carry, which I haven't done yet, but I noticed while I was working on my slides a couple days ago, so I'll probably do it. So I have a bunch of those, and I have tests that run on a lot of the arithmetic. And anytime I made the assumptions about arithmetic correctly, it's been fine. I haven't had to do anything. But I did have a week where 2's complement, which I was using in subtraction and a bunch of other stuff, was wrong, and I didn't know why, and it took a while. So we also have cartridges, and so in our previous picture we had this big block of memory, and that memory was just an array of bytes, and we would literally would address it by just going nth. And that's fine, but that's not really how this works. So we have a cartridge, and a cartridge is interesting because in most computers you think of a disk being just a sequential thing and they're standard, but the fun and weird thing about cartridges is that they have their own hardware in them. So if you want to do extra stuff with a cartridge, you can. So for example, I've implemented one of the cartridge formats, and that's NROM 0, and it is not fancy at all. So the interface for a cartridge is you have a lower bank, you have an upper bank, and then you have a little bit of RAM. And those banks are just ROM banks, so they're read-only. And If you want something fancier, like for example, each of those is 16K. So if you wanted more than 32K of space, then what you would do is you would have bank switching. So if you poked a certain byte in memory, then that would switch that bank over so that you could actually have more space. And also you could do weird animation stuff with it because you could have tiles that are very similar layered on top of each other. And then if you switch the bank, the tiles would animate, which is pretty neat. And there's a bunch of other stuff cartridges can do too. For example, battery backups for saves. There was, I think, the NES Zelda had save games on it, and if your battery died, you just lost your save. It was very sad. So I implemented the least fancy mapper, but the principles that I used to implement it should extend to everything. So it looks like this. So I have two protocols for parts of the system that read and write memory, and for each mapper, I just create a record that maps that memory to the for the desired cartridge type. And if I want to do fancy stuff like bank switching and whatnot, I can do all of that in the background. So I can just say, when you write here, also like low-key switch the bank. And again, I can show the specific code, but almost all of it is when we do a lookup, we just have a very large cond that says if the address is between here and here, look here, etc. Again, I'm happy to show anybody afterwards if they're interested. So with this in hand, I was able to make my first debugger. When I said that I am not a front-end developer by trade, I was not joking. But it's pretty cool, right? Like these are all just reagent cursors that point to various parts of state and memory. And on the right side there, I just console log the instructions. So this here is the initialization code for a particular ROM. And so the way that I debugged when I started was I would run this stuff and get the log messages out, and then some wonderful soul had disassembled and annotated one of the ROMs that I was testing against. So I literally just like emitted some instructions, and then I checked both of them to make sure that everything was like reading and jumping properly, which worked super well for a while, except for the fact that your emulator doesn't have to run like 10 instructions correctly; it has to run all of them. So I had to proceed to other testing methods. And so at this point, I decided one of the things that's sort of interesting about the CPU is that it really only does half the heavy lifting. And I wanted to make sure that I could solve the problems of synchronization because they're important. So so I started to write the picture processing unit, which I have drawn here. And it is a lot less clear how this works than the CPU. The CPU, because it is designed to be used by programmers, has interfaces that are documented. Everything about the PPU is reverse engineered. So I have probably 5 or 6 documents that explain how it worked, and I spent like probably 3 weeks squinting at them and wondering what I got myself into. But it's so the chip was called the Rico 2C03. It has a series of registers that are all memory mapped. Almost any I/O or interaction in the NES is memory mapped, so there's not a lot of direct memory sharing, which is actually pretty nice for our purposes. And so it has memory. It has 2 big registers, the cycle register and the scanline register, and it's something that I kind of had to implement by steps because there's a lot of stuff that goes on in there, but the PPU is more or less a fancy clock. So it keeps track of 2 main things. It has a cycle register and a scanline register. And so cycle is basically your x coordinate, and it ticks up every time the PPU runs for a cycle and goes from left to right. And then when it gets to the furthest right, it stops and resets again. So it's like the second hand of this clock, but it also goes left to right. And then we have the scan line is vertical. So this is like driving a TV directly. So we're thinking about this as being something that is sort of shooting beams and then advancing one and then doing that again. And so the cycle runs from 0 to 340, and the scan line we can think of as the minute hand, and the minute hand goes from 0 to 261. And not all of those coordinates actually are things that map to the screen. Some of them happen off screen, and the reason you do that is for synchronization, because again, it takes time for the beam to either reset from right to left again, or from bottom to top. So we have to account for that by adding cycles in there as well. So there's also a bunch of other stuff that's happening in here, and the PPU is, I don't really fully understand it yet, and there's a lot of stuff there. But the important thing that we need to know is that once every hour, basically, which in this case is 60 times a second. Time might have not been a great metaphor, but once cycle hits the bottom of the screen, it fires an interrupt to the CPU, which is called a V blank, or a vertical blank. And what that interrupt means is that it essentially is like, I have rendered a frame, go do some stuff. And almost all of the stuff that the CPU does, like anything that's time sensitive, if you're reading I/O, for example, I/O is all memory mapped. So to read from controllers, you just pull them 60 times a second every time this interrupt fires. Anytime you have timers for anything, like whether a platform's moving back and forth or something like that, that is all tracked in this interrupt. If you're using animation, also happens here. Audio happens here. Anything that's like real-timey is probably driven by a V-blank interrupt, because this is our clock, right? In a strange and backwards way, we're using the TV as the clock for the rest of our system. So there are three things that are hard about synchronizing these two things. One is that the PPU operates roughly 3 times as many times as the CPU does. In this case, the solution was not actually that bad. I literally have like a tiny vector in my state map that says PPU, 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 CPU, and I just rotate it every time. It's not fast, but it works. And then the second thing that's harder is opcode timing, because in addition to the fact that we have this ratio between the two, not every CPU operation takes the same amount of time, right? So we have to also simulate that. And this is one of the things where I was talking about how when you emulate something, it's not one-to-one, is because if you are really good at this and interested in a very accurate emulator, then what you are going to do is you're going to look at what state changes in every single cycle for each opcode and write those details. And that's a lot of work. Some people, it take like years to do it. It's a pretty difficult thing to do. And there are only a few cycle accurate emulators. I mean, part of it is even just finding the spec and knowing that on cycle 2 of an AND that these two registers change, and then later on something else changes. So you can have the opposite model, which is what I'm doing right now, where you can either commit all of your state changes at the very beginning and then just don't compute for the remaining cycles, which is what I do. Or you could also say, when this timer is finished counting down, execute the instruction. In theory, they should both work the same way, but it's not clear. And the third thing is interrupts. And interrupts are the first time I was tempted to reach for something stateful when I was modeling this thing. I was like, oh, cool, interrupts, they're like channels. I'll use a channel. And then I was like, wait a second, how do I serialize a channel? I'd have to just write something, take the byte buffer and write that down. I'm like, no, wait, I don't want to do that at all. So what I did instead is I literally just added another key to the state map that says, is an interrupt firing right now? And I just check it every cycle. And so with these two things solved, it's like, great, we're done, right? not really. Imitating things is very difficult. So this is a drawing of what my mental model of how this would go when I started working on it, which is that I would spend 50% of the time working on something that couldn't really run emulated software, and then the other 50% of the time would be sunshine and rainbows and really cool graphical glitches that I could post screenshots of. Unfortunately, that's not the case. It's an incredibly complex system. If one or two of your instructions don't work properly, then just things don't turn on. So it looks a little bit more like this. So where I am, I'm still somewhere outside of that slice. I'm working quite a bit harder than I thought I would need to for accuracy. But luckily, because I'm not the first person to ever write an NES emulator, a lot of people have had to solve this problem. And the way that people solve this is they write test ROMs. So they essentially write software for the machine that they then will run on either a known good emulator or on the system itself, and they'll see what the result is, and they'll use that as the spec for the system. So I started implementing one of the first tests, which is called nest test. And it runs about 8,000 instructions, and it logs every single line of the instruction, and that log contains some of the states. So to pass the test, you essentially have to make sure that your logs are synced up and that the timing is correct and the memory is good. And so this is what one of those log entries looks like. So I have an address, I have the bytes that I'm supposed to read, I have the op. I have the memory read, and then I have some register state. And then additionally, there are some cycle counts that are on the end of this log. I currently truncate those because I am working to get my CPU correct, and then I'm going to work on the synchronization next. So that's where I'm gonna go with it after this. But it's really interesting because this is not a kind of testing I've really ever done with something before. It feels like every time I pass a series of tests and get that one, I get another sort of layer closer to what the actual hardware is. And in so doing, I've now made my system precise enough to run another test. So for example, I can now run these test ROMs and do that comparison. So that means that most everything is working properly, but there are a ton of very, very small details that you have to sort of suss out. For example, one of the last ones I fixed is what happens if you were reading something that works on, there's a concept in the memory called the zero page, which is it's the first piece of memory between 0 and FF. And if I read an address at FF, an address is 2 bytes, so do I read out of the 0 page or do I wrap around? And the answer is that I wrap around, but there's no way I would have known to look for that until I saw a test that said, hey, I bet you're not testing for this. So I have the skeleton of a CPU. I'm currently fine-tuning, or of a PPU, sorry. I'm currently fine-tuning the CPU for accuracy and fixing bugs. The previously mentioned test, nest test, I'm about 3,000 out of 8,000 log entries correct. To give a little bit of context for that, there are a lot of emulators that never pass that test. Which is another one of those things that makes this really interesting, right? Is that the sort of, we judge an emulator by how well it runs software. We don't necessarily care about the details. So there are emulators that have been in the wild for like 20 years that still aren't technically correct, which shows us probably some things about correctness in software. So here's some stuff I learned. I learned a lot about low-level computing. I thought I understood register machines. It turned out I didn't. Now I understand a little bit more, but it's really, really interesting stuff. I've had a lot of fun with it. The one big atom model is great, and it works. And every time I tried to separate something out because I thought, maybe these two things shouldn't be able to write to the same map because they don't technically share memory in the actual system. Every time I had that thought, I would be burned by the fact that this model was no longer simple. And so keeping everything in one place actually works really well. And the time travel stuff works pretty well so far. I've debugged a lot of problems with like that debugger that I showed you before. Fixed a lot of stuff with that. It doesn't look very nice, but you can go back to when things were wrong. It's the sort of the same thing as like the Clojure script development feeling, right? You can just go back, work through a problem, stop and do it again, and just sort of like be in flow, I guess, the entire time. So it's working pretty well, and software archaeology in general is super fun. I really like this stuff. I wonder historically if we are going to be very good at documenting a lot of the things about the systems that we've built. And I know that there are librarians and architects specifically, or not architects, but librarians and archaeologists who are interested in this particular thing. Like, if I put code from something in a museum, does that actually technically count as archival if I have a printout of something? Or does it have to be the dynamic artifact? Like, how do we actually capture that history? And not only that, but you have to figure everything out by reverse engineering or testing or sort of poking through stuff. Emulation is not magic, I'm happy to report. Thought it was magic, it's not magic. It's really interesting. It takes like a lot of thought and work, but it's great. And I would encourage anybody who's even thinking about doing a little bit of emulator stuff to dive in. And I'd be happy to talk about it after the fact as well. So I think that's what I've got. I'm Angus, I guess, on Twitter. I have all of the code up on GitHub. It's under very heavy development right now, but I'm certainly happy to accept patches. I have some ideas for future work. I've been talking. I'm thinking about making it CLJC, because really the only thing that won't port directly over is probably the arithmetic, and that's just because of data type stuff. And I've prepared a bibliography as well. And that's on git.io/time travel, which has links to almost everything that I used to make this, and also some books that I read and liked that got me to do this project in the first place. So thanks so much.